Welcome back. In our previous lecture, we were talking about equivalent states, and given a DFA with a transition like this from state P on input W and another state Q on input W on the same input string. Okay, these two states are said to be equivalent if this transition gives us a state, say R, and this gives, say, R dash, and both R and R dash are either final states or R and R dash both are non-final states. So it cannot be that R is a final state and R dash is a non-final state. So if these conditions are satisfied, then we say that P and Q are equivalent. And if the states are equivalent, then we can combine these states. And also we had looked at the concept of K equivalence. So if the length of W is 0, then we say that the two are 0 equivalent. If length of W is 1, then we say it is 1 equivalent, and so on up to K equivalent. So K can be any number. Now coming to our minimization problem, minimization of the DFA. So we saw that if a state is unreachable, then we can remove those states. And if two or more states are equivalent, then we can combine these states. So that will give us lesser number of states as the original DFA. So let us take a problem. Let us have a DFA. So I have 0, then I have 1, then I have 2, 4, 3, and 5. So on 0, this goes to here, and this on 0 goes to this. 3 on 0 on 1 goes to 3, and 1 on 1 goes to 3. 3 is a final state, 5 is a final state. And here I have 2 on 0 goes to 1, and 2 on 1 goes to 4, and 4 on 0 or 1 goes to goes to 3, and this also goes to, on 0 and 1 it goes to this, and 5 on 0 and 1 it goes to this. Now let us see if there are any unreachable state. So if we look at this diagram or this DFA, we'll find that all the states have some arrows entering it and some arrows leaving it. But state 2, you can see only that it is only 2 arrows which are true transition out of this state. No transition into this state. So you cannot reach this state from the start state. So 2 is a unreachable state. So this is directly it is unreachable. Now if we look at this a little bit more, we will find that state 4, you can enter state 4 only through 2, only via 2. State 4 can be reached only via 2, but you cannot reach 2 from 0, from the start state. So 4 is also unreachable. So 2 and 4 are unreachable states. So let us remove these states. Okay, so let me just remove these states, 2 and 4. So like I had mentioned earlier, we can remove the unreachable states. So we are left with 3 and 0, 1, 3 and 5. So out of 6 states, we are now left with 4. Now let us look at equivalence. So to compute the equivalence, we'll follow this approach. So the first thing that we do is we are going to partition our states into 2 sets. The first set will consist of final states and the other will consist of non-final states. So our states can be written like this. So 0 and 1 are non-final states and 3 and 5 are our final states. So we have 2 sets of states, and this actually is nothing but our 0 equivalence. I'll just write E. So 0 equivalent states. So 0 and 1 and 3 and 5. Okay. Now what we will do, we start with this, partitioning the final states and the non-final states. Next we will find which of the states are 1 equivalent. Okay, and if you can recall, 1 equivalent means the length of W here is 1. So after reading one input symbol, if the 2 states are again, they reach the state R and R dash, and R and R dash are in the same set, then we say that they are 1 equivalent. So let's take 0. So we have only 2 here, so let us take 0 and 1. So 0 on 0 goes to 1. I think it is better if I draw the transition table. So I have 0, 1, 3 and 5. And 2 input symbols, 0 and 1. So 0 on 0 goes to 1. 0 on 1 goes to 3. Okay. And 1 on 0 goes to 0. 1 on 1 goes to 3. Then 3 on 0 goes to 5. And 3 on 1 also goes to 5. And 5 on 0 goes to 5. 5 on 1 also goes to 5. Okay, so now from this transition table, let us see if there are any 1 equivalents present here. So let us take 0 and 1. So 0 is our start state and 3 and 5 are our final states. So 0, from 0, you can see on 0 it goes to 1, okay, and 1 on 0 goes to 0. So both of these are in the same state here. Both these two are in the same state here. So no problem. Let us look at 1. So 0 on 1 goes to 3 and 1 on 1 goes to 3. So again 3 is also, they go to the same state. So same state, then I don't have to worry about it. So I can say that 0 and 1 are 1 equivalent. Now we don't have any more states. So 0 and 1, we say that it is 1 equivalent. Next, let us look at the next set, that is 3 and 5. So 3 on 0 goes to 5. 5 on 0 also goes to 5. So it goes to the same state. So no problem. And then 3 on 1 goes to 5. And 5 on 1 also goes to 5. So it's the same state. So 3 and 5 again are 1 equivalent. Now if you look at this, you will find that from the first step and the second step, there has not been any change. The sets are the same. So what we can do is, we can now combine the states. We can now combine the states.